Hi, welcome to part 4 of the Photodiode series. In this video, we will cover the noise analysis of the Photodiode amplifier circuit. Let's begin with a brief overview. Here we have a Photodiode amplifier circuit in the photovoltaic implementation. This circuit converts electrical current from a photodiode to an output voltage. To calculate the output voltage, we multiply the input photodiode current times the feedback resistor. Keep in mind that the output voltage generates noise. So there are three important factors that are related to the output voltage noise, and it will also determine the circuit bandwidth. These are noise gain, noise bandwidth, and signal bandwidth or cutoff frequency. The first two contribute directly to the overall output voltage noise. The last one is dependent on the feedback resistor and the feedback capacitor, and will determine the cutoff frequency, which is also linked to the noise bandwidth. The next step is to locate the noise sources. We can split the circuit into three separate sections: the photodiode, the feedback loop, and the op-amp, where each section generates noise. Then all the sections will be combined to compute the total output noise voltage. The noise will be determined by the input capacitance, which is the sum of the junction capacitance and the capacitance of the op-amp. And to get the capacitance of the op-amp, we need to sum the common mode capacitance and the differential mode capacitance. We also need to get the feedback capacitance, the shunt resistance, and the feedback resistance. All of those elements will determine the noise output and the noise gain. The next step is to get all the parameters needed for all three sections. Let's begin with the op-amp. Go to the datasheet of the MCP6491 op-amp and get the parameters such as common mode, differential mode, gain bandwidth, noise voltage density, noise current density, among other things. Also, using those values, you're going to have to do some addition to get other values. Now, to get the parameters for the feedback loop and the photodiode model, let's look at the circuit of the Photodiode amplifier circuit and the datasheet of the photodiode. The junction capacitance is 100 puff. The shunt resistance is at 2000 mega ohms. The feedback resistance is 10 mega ohms. And the feedback capacitor is 1 puff. Now, the Photodiode amplifier does not always behave as desired. The gain peaking and step-out ringing are typical phenomena which could happen in frequency and time domains. The noise gain peaking results in very high output noise levels, which may severely degrade the integrity of the output signal. This phenomena can make the Photodiode amplifier very unstable. To fix this, a small capacitor can be added in the feedback loop to eliminate the gain peaking, step-out ringing, and the noise gain peaking issues. Next, let's go over the stability of the Photodiode amplifier and explain why the amplifier will be stable after adding the feedback capacitor. The figure on the screen shows the noise gain body plot of the Photodiode amplifier in a log scale. It is important to clarify the difference between noise gain and signal gain because the system stability is dependent on the characteristics of the noise gain and not the signal gain. The stability of the system is determined by the net slope between the noise gain and the amplifier open loop gain at the frequency where they cross over. For an unstable Photodiode amplifier, the net slope between noise gain and amplifier open loop is equal to plus 40 dB per decade as shown on the graph, where the dotted line of the noise gain intercepts the curve at the open loop. The dashed line shows the extended noise gain curve without adding the feedback capacitor. On the other hand, for a stable Photodiode amplifier, the net slope between the noise gain and open loop is equal to plus 20 dB per decade as shown on the screen. Where the solid line of the noise gain intercepts the curve of the open loop, the solid line shows the noise gain curve with adding the feedback capacitor. So let's explain this noise gain body plot a little more in detail. This is where we're going to find the frequency parameters that we need for the noise analysis. F1 represents zero frequency and is determined by the feedback resistor and the input capacitance. F2 is the signal gain bandwidth or the cutoff frequency, which is determined by the feedback resistor and the feedback capacitor. F3 is the noise gain bandwidth, which is a noise gain and open loop gain intersection frequency. Now let's go over the frequency parameters. Okay, so when F is less than F1, the noise gain is equal to 1 plus the feedback resistor over the junction shunt resistance, which is roughly equal to 0 dB. The zero of the noise gain is located in F1. When F is between F1 and F2, the noise gain increases by plus 20 decibels per decade. The pole of the noise gain is located in F2, which is equal to 1 over 2 pi times the feedback resistor times the feedback capacitor. This is also the signal gain bandwidth. When F is between F2 and F3, the noise gain is equal to 1 plus the junction capacitance plus the operation amplifier input capacitance over the feedback capacitor. The crossover frequency of the open loop and the signal gain is located in F3, shown on the equation below. Now, when F is larger than F3, the noise gain is determined and limited by the open loop, which decreases by negative 20 dB per decade. The value of the feedback capacitor affects the location of F2, which determines the signal gain bandwidth and the phase margin of the photodiode amplifier. Now, to complete this table, we need to get the 1 over F noise and the broadband noise intersection frequency. To do that, we need to get some values from the datasheet of the op-amp, such as 1 over F input noise voltage density, the lower end frequency, and the input noise voltage density. Then we plug in the values, solve for the equation, and we get the frequency parameter for F4. Now, we need to calculate all the parameters before we begin with the noise analysis. To calculate the noise gain, we simply substitute the capacitance values from our circuit and solve the equation below. Then, to calculate the cutoff frequency, we substitute the feedback resistor and the feedback capacitor and solve for the equation. Then, to calculate the noise bandwidth, we need to multiply the brick wall conversion factor for a first order system such as this times the noise bandwidth. And finally, to complete this table, we need to calculate the noise gain bandwidth. We do this by dividing the gain bandwidth product of the op-amp over the noise gain. So now that we have all the parameters and collected all the information from the data sheets and the circuit, let's focus on the noise analysis of the photodiode amplifier. Like we mentioned before, there are 3 noise sources on the photodiode amplifier circuit. Let's begin with the feedback loop. To calculate the thermal noise voltage from the feedback resistor, we need to calculate the resistor voltage noise density. We just follow the equation below where K is the Boltzmann constant, T is the absolute temperature in kelvins, and the value of the feedback resistor of our circuit. We plug in the values and solve for the equation. Then, to get the resistor thermal noise voltage, we multiply that answer times the noise bandwidth of the circuit. Next, we need to calculate the total RMS output noise voltage. To do that, first let's get the photodiode noise current values from 3 different noise sources, such as the shunt resistance, the dark current, and the light current. In our circuit, we have the shunt resistance of 2000 mega ohms. We plug that into the equation and solve it. The thermal noise of the shunt resistance is 28.68 femtoamps. Now, to solve for the dark current, we're going to use this value that we previously got from the op-amp's datasheet. We're going to plug it into the equation, and the shunt noise due to the dark current is 25.3 femtoamps. And then to solve for the light current, since there's no light for this circuit, we're just going to leave it at 0. So now, to get the total photodiode noise density, we plug in the shunt current, dark current, and light current values that we just calculated. We plug it into this equation, and the current noise of the photodiode is 38.24 femtoamps. Now, to get the total noise current spectral density, we're going to use the current photodiode noise value that we just calculated and the input noise current of the op-amp. Remember that we got this value from the datasheet. Then we plug these values into the equation below, and the noise spectral density is 38.2447 femtoamps. Now, the total output noise voltage spectral density is calculated by multiplying the total noise current spectral density times the feedback resistor. This gives us 382 nanovolts. And finally, to get the total RMS voltage output noise, we multiply the value that we just previously calculated times the square root of the noise bandwidth of the circuit. So the total voltage noise RMS output is 6.039 microvolts. Next, let's calculate the op-amp's noise voltage. To do that, we're going to need a table with all the parameter frequencies we previously made. Here we have all the 5 different regions with its formulas. all you gotta do is substitute the values that we previously calculated and this value right here that we got from the op-amp's datasheet. Solve for the equations and then plug in those values in the following equation. The total RMS output noise voltage is 797.7 microvolts. So now that we have the total output noise from all three different sections, let's calculate the total output noise voltage of the entire system. To do that, we simply get the total RMS noise voltages from the feedback loop, the photodiode, and the op-amp. We plug those numbers into the equation, and the total output noise voltage of the entire system is 797.7 microvolts. Thank you for watching.